In this video, we are going to look into the properties of Fourier transforms, that is continuous time Fourier transforms. So in the preamble, let us revisit the definitions, that is the Fourier transform and the inverse Fourier transform. So for the Fourier transform, x of t can be converted or transformed to x of omega or x of j omega by an integration, and integration is from minus infinity to infinity exponential to the power minus j omega t dt. And the inverse, from a minus now you have a plus here in the exponential, and the integration is with respect to omega rather than t, and eventually we will get back our x of t. In a previous video we have mentioned that if x of t is periodic, the Fourier transform is simply the coefficient ak of that periodic signal multiplied by 2 pi delta of omega minus k omega naught. So we can easily take the Fourier transform of a periodic signal if we know the Fourier series coefficients. So in this video, let us consider a signal x of t. This may be an input signal. So if x of t has a continuous Fourier transform which is x of j omega, then y of t is also having a continuous Fourier transform which is y of j omega. So in this case, the linearity property states that a constant value a multiplied by x of t plus a constant value b multiplied by y of t. So this has a Fourier transform in terms of x of j omega, y of j omega, and multiplied by the coefficients. So let us move towards the proof of this property. So specifically, we are interested in taking the Fourier transform of a x of t plus b y of t. So from the definition, we would take the integration, and for that we have a x of t plus b y of t multiplied by exponential, which is minus j omega t dt. And since integration is a linear operator, we can break this summation into two separate integrations. So the first would be a minus infinity to infinity x of t e to the power minus j omega t plus b integration minus infinity to infinity y of t e to the power minus j omega t dt. So we have extracted out a and b because they are not dependent on time, that is dt. But over here again, this is just a definition of the Fourier transform, that is, this is simply x of omega or x of j omega, and similarly this is y of omega or y of j omega, and they are multiplied with a and b, and then we have this plus. It's a very simple and straightforward proof, but it finds many applications. For example, say x of t is e to the power minus 2t u of t, and y of t is e to the power minus t u of t. So it's a very common and a fundamental signal which we have already proved in a prior video. So the Fourier transform of x of t and y of t are as follows. Now let us say a and b are just 1, so we are interested in subtracting y of t from x of t, that is, we are having a value which is x of t minus y of t. So this is our new signal which is z of t, and we are interested in finding the Fourier transform of this z of t, that is, we are interested in z of omega. So this would be simply 1 over j omega plus 2 minus 1 over j omega plus 1. So by taking LCM, we would have j of omega plus 2 times j of omega plus 1, and in the numerator we would simply have just a minus 1, and then we can simplify it further. So next we have a time shifting property, that is, if we are shifting in time x of t minus t naught, then we would be having a coefficient that is e to the power minus j omega t naught multiplied with x of j omega. So let's move towards the proof of this property. So say we have g of t which is x of t minus t naught. We take the Fourier transform of this, so we have g of that is a minus infinity to infinity x of t minus t naught e to the power minus j omega t dt. Now let us say we use a change in variable and we set tau which is equal to t minus t naught. So in this case we would have x of tau e to the power minus j omega tau plus t naught dt, and since the limits of integration are from minus infinity to infinity, they would not be changed, so we would simply have a minus infinity to infinity. Now this t naught is not a part of this integration, so we can take it out of the integration, so we would have e to the power minus j omega t naught, and rest of the function would be an integration of x of tau e to the power minus j omega tau d tau. And this is simply a definition of Fourier transform. So we have x of omega or x of j omega, which is now multiplied with e to the power minus j omega t naught. So this concludes our proof, which is mentioned over here. So as an example for this property, let us include this function. So we are asked to find the Fourier transform of x of t, which is shown in this figure. There are several ways to solve this problem, and we have used time shifting property over here. So what we have done is we have broken down this signal into two parts. The first part is this signal, and the second part is this signal. So the green signal is expressed over here and it is having an amplitude of 1. Also this green signal is scaled to origin. So if the center point was at 2.5, so we are shifting this 2.5 to 0. So as we would subtract 2.5 from 4 and from 1, so if we subtract 2.5 from 4, we have a 3 by 2, and from here we would have a minus 3 by 2. So this is our 0, and we term this signal as x2 of t. Note that later on it would be reverted back to its original position by a shift towards right, that is x2 of t minus 2.5. That is, this signal would be simply at 2.5, and that would be a square wave having an amplitude of 1. Similarly, the yellow signal is mentioned as x1 over here, and this is also moved from 2.5 to 0. This is over here. Moreover, we subtract 2.5 from 3, so we have 1 by 2 and a minus 1 by 2 at respective edges. So now this is again a square wave, and you note that we have actually this part that we desire, which starts at 1 and terminates at 1.5 in the amplitude. So hence we scale it by 1 by 2. So therefore this x of t, this signal, is represented in terms of x1 of t and x2 of t by this expression. That is, x of t is 1 by 2 x1 of t minus 2.5 and x2 of t minus 2.5. Now the Fourier transform of x1 of t, this is mentioned over here. A square wave would have a Fourier transform which is a sinc function, and similarly x2 of t would have another sinc function which is over here. Note that this was without time shift, that is this t minus 2.5. So hence we apply the time shifting properties and perform the linearity because there is a summation here. So eventually it is quite easy to prove that we would reach this expression. The next two properties are scaling in time and flipping in time. The proof of this is very similar to the proof that we have performed for the Laplace transform. And you just need one change in variable to achieve this and this expressions. So we would not perform those over here, but a very important intuition is that if we are having x of at, so say we have a signal which is x of t, and that is a square wave, and the transform of this is simply x of omega, which would be a sinc function. Now if we compress this signal, that is we have x of t by 2, so hence this signal would now be half of the duration from the above signal in time, but in frequency it would be expanded in time. That is, now your first lobe would be far from the initial point of here. The first intercept would be here rather than here. So we are expanding in frequency as we are compressing in time. And of course the reverse would also hold. So next let us look into a convolution property, and we'll start with the proof as usual. So we are interested in the Fourier transform of x of t convolved with y of t. And this is simply minus infinity to infinity x of t convolved with y of t exponential e raised to power minus j omega t d. But we know that x of t convolved with y of t, this is simply x of tau y of t minus tau minus infinity to infinity d tau. So we would have a minus infinity to infinity, yet another integration minus infinity to infinity x of tau y of t minus tau e to the power minus j omega t d tau and dt. So this is simply t because we are having the Fourier transform and not the inverse Fourier transform. So now this is a double integral with two variables of integration, that is one with tau and another one with respect to t. Now bringing the integration, the inner integration, that is with respect to tau, this integration outwards, so we have a minus infinity to infinity x of tau, and then this integration which is from minus infinity to infinity y of t minus tau e to the power minus j omega t dt and d tau. So next we will use a change in variable. In the fourth equality, and we set a t tilde which is equal to t minus tau. So hence we have a minus infinity to infinity x of tau integration from minus infinity to infinity. These would be unchanged because the original limit is starting at minus infinity and it is going to infinity. So anything added or subtracted from infinity would remain the same. So we have y of t tilde e to the power minus j omega t tilde plus tau from here dt tilde d tau. Now this tau is not a part of this integration, so in the fifth equality we can extract it out. So that is, we would have a minus infinity to infinity x of tau and then e to the power minus j omega tau, and then the inner integration which is a minus infinity to infinity y of t tilde e to the power minus j omega t tilde dt tilde d tau. Now this is just a simple definition of our function, which is y of omega or y of j omega. So as in the sixth equality we have minus infinity to infinity x of tau e to the power minus j omega tau d tau times y of j omega. And again this is just a standard definition of the Fourier transform of x of tau. So we have x of j omega multiplied by y of j omega. So this concludes the proof of our convolution property, which is mentioned over here. So next we have the differentiation property, and let us move towards the proof of this property. So we know that the inverse Fourier transform, that is x of t, is simply 1 over 2 pi minus infinity to infinity x of omega e to the power plus j omega t d omega. Now if we differentiate both sides, that is d by dt x of t, and on this side the differential is only with respect to the exponential, so we would have 1 over 2 pi minus infinity to infinity x of omega d by dt exponential of j omega t d omega. And if we differentiate the exponential, this argument would come as a coefficient, so we would have j omega times 1 over 2 pi minus infinity to infinity x of omega and the function itself, that is e to the power j omega t d omega. And this is exactly same as our initial starting point. So hence if we are differentiating in time, we are just multiplying by j omega, and this is appearing over here. So by the same way, we can also prove the differentiation in the frequency domain rather than the time domain. Now let us move towards a very important property, that is an integration property, and we move towards the proof of it first. So we have a signal which is g of t, and this is simply minus infinity to t x of tau d tau. But this signal g of t has an alternate representation in terms of the convolution, that is we have a signal which is x of t, and this is being convolved with the unit step function u of t. So these two are equivalent. So this is our g of t. Now the Fourier transform of g of t is the Fourier transform of x of t times the Fourier transform of unit step function u of t. That is, convolution in time has a pair of multiplication in the frequency domain. So from here, this is simply x of omega, and this is multiplied with the Fourier transform of a unit step function, and this is derived in another video. So simply I'm writing the solution, which is 1 over j omega plus pi delta of omega, so which is also appearing over here, and this concludes our proof. Now in order to understand this property further, let us look into one example. Say we are given with a signal x of t, and this is an odd signal which is passing through a region, and it has this shape. It is starting at -1 in time and terminating at +1. The amplitudes are +1 and -1 respectively. So for x of t, we are asked to find x of omega, that is its Fourier transform. Now there are several methods by means of which we can do it, but the simplest one is by using the differentiation and the integration property. Let us differentiate this signal, that is we have x dot of t. So if we differentiate this signal, we would have to consider few aspects. The first is that there are two discontinuities, one is over here and another one is over here. So for discontinuities, we would have some impulses, and at this point at -1, that discontinuity is basically having a strength of -1. So at time instant -1, we have a discontinuity which is in terms of direct delta function, and it has a strength of -1. Similarly, this function at +1 has a discontinuity which is again having a negative slope, so it has a direct delta function of strength -1. So far we have just covered this and this discontinuity. So let us call this discontinuity function as g1 of t. But we have not covered this signal in terms of differentiation. So we have to add this signal with another signal, that is g2 of t, which would be simply y2 minus y1 over x2 minus x1, that is a slope. So from -1 to simply +1 in time, we would have a signal which is +1. So in short, this has a differential in terms of these two signals, impulses and a rectangular function, that is x dot of t. This is simply equal to g of t, which is equivalent to g1 of t plus g2 of t. Now taking the Fourier transform, that is g of omega, this g1 of t is simply impulses which are delta of t -1 and delta of t +1. So these shifted impulses have a transform which is e to the power plus j omega, and from here we have e to the power minus j omega. So this was a minus here, so we have a minus and a minus. So this is g1 of omega. Similarly, for g2 of omega, we can have a plus over here, and this function, the square or a rectangular function, has a transform which is simply 2 sine of omega over omega. Now using the Euler's identity, we can simplify this as a -2, and we are multiplying by 2 and dividing by 2, so 1 by 2 e plus j theta plus e minus j theta is simply cos theta, so we have a -2 cos of omega plus 2 sine of omega by omega. So this is our g of omega. Now from the integration property, we have x of t, which is in terms of -infinity to t, g of t. The integration is with respect to g of tau d tau, and hence this would be paired with 1 over j omega g of j omega plus pi g of j0 delta of omega. So hence to find the Fourier transform of this, we are using the integration property. G of j omega is already given over here, so let us plug that in first. So from here we have x of omega, which is simply a -2 cos of omega over j omega, a +2 sine of omega over j omega square, plus let us call this as this term 3. This is term 3. Let us find the value of this term 3. So you can observe that the value of term 3 depends on g of j0, or simply g of 0, and this indicates that we are interested in the DC value. Now if we directly put 0 in this equation, that is this equation, we have cos of 0, which is simply 1, and then we have a sine of 0, which is 0, but omega is also 0, so this will be a problematic thing to solve. So we go to an alternate approach, that is this intuition that DC is just an average value of a given signal. So coming back to g of t, which is just a summation of these two signals, this whole thing is g of t. Let us start with g2 first. So the average value of this signal is simply a 1 multiplied by a 2, that is the area of a rectangular function. So this is simply 2. So the area for this is just 2. Now the area for this, the area of this function is a -1, and the area of this function is again a -1. So this is also -2. Moreover, this g of t is adding these two areas together. So the DC value or the average value is dependent on this plus this. So -2 plus 2. So eventually we have g of 0, which is equal to 0. Now if this is equal to 0, this means that whole term 3 is equal to 0, because now this is just 0. So our Fourier transform is simply this function. So do note that you are going to obtain this by an alternate method also, which I'm just going to point out, that if you find the Laplace transform of this signal, and then you set sigma equal to 0, that is the real part equal to 0, so you would have the Fourier transform. So why is it so? Because this signal is converging, it's absolutely integrable. So if it is absolutely integrable, it follows the Dirichlet conditions, and simply by plugging in sigma equal to 0, we will get this result. The next property is the Parseval's theorem, and over here we have the energy of a signal, that is the total energy, which we calculate by taking the absolute square of a given signal and then integrating from -infinity to infinity. So this gives us the total energy of a given signal in time domain. But we can also find the total energy by finding the square of magnitude spectrum and then integrating it from -infinity to infinity, and then scaling it by 1 over 2 pi. So let us look into one example. Say we have a signal and its spectrum is given by so this is x of j omega. This value corresponds to under root pi, and this is simply pi by 2 under root, and we are asked to find the energy of this signal. Now using the Parseval's theorem, we can solve this integration by simplifying, such that we break this into two parts. We have a function which is on the right side, and the same function is also on the left side, so that is, this is an even function. So hence we can convert this into an integration from 0, starting from here until 1, and then multiply it with 2. So we have 2 times this function, that is 1 over 2 pi, 1 over 2 pi, and integration from 0 to 1. And let me call this function, the one in green, as g of omega, which is just this right sided signal. So this is g of omega, and we need to take the square of it, d omega. So this is a simple thing to solve. we know that we can find the area of this function by dividing it into two blocks. So the first block is this one, the yellow block, and the second block is the bigger block. So therefore the solution of the yellow block is its length into its height. So length is simply 0.5, and note that we have to take the square of height. So this was simply under root pi by 2, so we can take pi by 2 whole square. Similarly, for the second block over here, again the length is 0.5, which would be multiplied by the height. So that is simply under root pi, but we are taking a square of it, so we have pi square. And these coefficients would simplify, and we would have simply 1 by pi. So therefore this result can be simplified further, but anyways this yields the solution of total energy for this given signal. So therefore this signal, which is represented as, this is zero frequency and we have omega. So at a given angular frequency, say this is simply omega reference, omega r. So what is the energy content in that? We can find it at that particular frequency. So overall, the energy in the whole spectrum is found by taking the integration from this point until this point, which we have performed over here. So these are some of the fundamental properties of Fourier transform. In the forthcoming videos, we have two more very fundamental and very applicable properties. The first one of these properties is the duality property, and the second one is the modulation property.